This is Cristian Jimenez,
and Héctor Martinez,
and we are going to present the assignment number 2 of computer applications for power systems. The main objective of this assignment, we created a default code which will allow us to classify the learning set analog values by using the K-mean algorithm. Then after running this algorithm, we will apply the second algorithm, KNN, in order to classify the test set, which means the measurements. The results will be shown as pictures, and the pictures will be located in the assignment folder. So first, after we got all the information provided in CSV files, we will start extracting them in order to manipulate this data and to run the algorithm. So we create a function called extract data, which initially looks for the file path, which means the documents folder, and read it and extract them as a list. This kind of list will be arranged by points. One point will have two features, which means the voltage and the angle. It will be the same done for all the buses. In our case, we have 9 buses. And after all this information is arranged, then we can start proceeding to start with the first algorithm, which will be a K-mean algorithm.
For the K-mean algorithm, we have the code here. We import our libraries that we're going to use. NumPy is a library that is really useful to calculate Euclidean distances and make life really easier when it comes to execute this function or these mathematical formulas. So first we define our K function. We're going to receive the number of centroids that we want to have. In this case are going to be 4. We receive the point list train and the point list test. The first thing we're going to do is execute the K-means algorithm. So we assign the number of centroids. We assign randomly these centroids, assign some colors, and after this we're going to execute locate centroid, which after just locating the centroids in a random way, we're going to use a little bit of this formula to locate them in good positions, because if we just keep random positions at first, the algorithm doesn't run really well. So what we do is just to try to distribute them equally or in points not really far away than from the measurements that we have. After we have our located centroid, then we execute our function of point to cluster. In this case, we can have 2. We can classify the points with K-means or KNN. The only thing is we just need to uncomment this one, but in this case we just go directly with the train. So point to cluster, we have the condition where what is not stop, it will continue. So for every point in our point list, we're going to assign it to a cluster. With this function, assign to cluster, we go here, assign to cluster. Basically this function, what that is going to do is to return the closest cluster to the point. So we establish our distance, and then we iterate over each centroid, and here is where we calculate the Euclidean distance. This is the formula that we use with NumPy, linganag.norm. So we have the centroid, the position of the centroid minus the position of the point is going to give us a distance. Then after that, the closest cluster is going to be the minimum of these distances. We return the closest cluster. We return to our function here, and then the closest cluster, here is where we're going to all the points that we found that are like closer to this cluster, we're going to append to it. We're going to add them. Then we're going to do this with all the points, and after that, this is our condition to stop. So basically, here is what we're doing is we're going to check if the clusters. Oh well, if the condition is not to stop, then we're going to go to relocation. This is what it's going to do. It's going to relocate our centroids. Here is a function. So basically in this function what we do is from the actual points that we have, we're going to just make a summatory of the points in X, then a summatory the points in J, and then after that we only get the mean value of every one of them, and this is going to be the new position of the centroid. Then when the condition here, that basically this condition what it's going to do is going to check that if the actual points of the centroid hasn't changed, because it's, I forgot to mention, here we just reset the actual points. So this means that the actual points are going to be now our last points. Then we just empty the actual points, and this is going to be determined by this condition. If the points in the centroid they didn't change, or they didn't change in length, or they didn't change in the content, then the reset is going to be false. So basically we're going to stop when all our points has been assigned to the centroids have been relocated and then haven't changed. Then after this, having now from the point to cluster, we have the function plot graph. The plot graph is just going to just go over the centroids and its point, and is going to draw them. We use for this function the library of matplotlib. And then what is important, and to finish this algorithm, is to have, and it's going to help us with the KNA algorithm, because we need to remember k-means is an unsupervised algorithm and KNN it's a supervised algorithm. So in order to achieve that, we need to put some labels on it. So the function of labels is here.
So now, in order to assign the proper label for the clusters, it's important to mention that we will have 4 different labels: high load, low load, generator shutdown, and line out during maintenance. So in order to know which label, or I mean which cluster correspond to which label, the next explanation is well to know it. So for high load and line and low load, it is known that when the load is demanding a high amount of energy, which means the generator is injecting too much current, there will be a high voltage drop across the transmission line. So therefore it is expected that the value at the receiving point, which means at the load point, will be lower compared to the sending point, which means the generator. By the opposite, when the load is really low, the voltage is expected to increase, which means to be high. By knowing this one, we will proceed to calculate the average centroid of every cluster. For every time, we have 4 different clusters. And now that I have already explained about the high load and low load, we calculate the average of the 4 clusters. The cluster with the highest voltage magnitude, it will be tagged with the label low load. By the opposite, the cluster with the lowest voltage magnitude will be called as a high load. Now 2 labels have been assigned. The next label will be the one for the generator down. In our case, we have 9 buses. 3 of them are classified as slack bus or PU. When a generator is out of operation, which means shut down, in that connections between contiguous buses, theoretically they are at the same voltage levels, as well as the phase angle are the same, which means that there is no power flowing through that line. So in order to know which is the following cluster with the tag of a generator down, we will calculate the average phase angle of the 4 clusters. The cluster which has the phase angle equal or at least the value nearest to 0 will be assigned with this cluster, which means generator down. For the last label, which means the line out, it is known when a line is out, the path that the current will follow to reach the load will be larger, leading to a higher voltage drop. As the path is larger, the total impedance of the path is also higher, so that we can know if any cluster will be tagged as line out. It will be also to require to calculate the voltage drop. The one with the highest voltage drop will be line out, but as previously we have assigned the 3 cluster, the one which is left will be automatically done or called as a line down.
Now for the KNN algorithm, we have the code here. What we need to do is, now that we have our labels, and here we go and call it, after plotting the graph, we just send them. So what we can do is just send the test set that we have. We have our centroids, so we're going to send that one. And then in the KNN, what we're going to have is just, we need to find where is the nearest neighbor of all of them. So what we're going to do is we're just going to take the point and we're going to start comparing with all the other points that we have found that they are already assigned in the centroids. And we're going to, this is based on votes. So we have 5 votes in here. It's always good to have non-parity number. So first we're going to find the neighbor, and after finding the neighbor, what we're going to do is we're going to calculate all the distances. We're going to save all these distances also with the centroid level, because we need to know which one is according to which one. And then we're going to say it to a trial. So basically in this trial, what we're going to do is we're going to count the votes, or we're going to see how many votes all of them got regarding the shortest distance between the point and the centroid. After this list, we have this list. We're going to have this verdict where we're going to have this function called trial. After having all the votes, what we're going to do is we're going to take the one that have the most votes, and we're going to assign it to that centroid. So what we can see here, if we execute, first we get the values from the analogs, from measurements, then we execute k-means. K-means is actually pretty fast. Then it's going to take a while for us to finish with the KNN means, and as initially mentioned, the results are going to be graphed and going to be saved in the root folder of the program. So we wait a little bit, and after that, when this is finally executed, we're going to have the results here, which is k-means algorithm and KAN algorithm. PNG is how we called it. So we have now that it's finished. So we can now open, this is the k-means algorithm and the KNN algorithm. Thanks for your attention.
Thank you for your attention. Thank you for listening to our video.